Good evening, everyone. It's wonderful to have you all here tonight. We're delighted to welcome Chris Madsen, who will be sharing his insights with us on load balancers. Chris, please, the floor is yours.
Awesome. Thanks, Felipe. Good evening, everybody, and thanks for coming out tonight. My name is Chris, and I'll be speaking to you tonight about load balancers and their role in system design and computing. Before we get started, I would like to thank Scismic for sponsoring tonight's talk. All right, so load balancers, they're a critical part of system design and architecture. Before we get into some of the details, though, it might be helpful to start with an analogy to kind of illustrate the concept. This is not mine, borrowed from a couple of sources, as it seemed to be a common way to think about this topic. For this analogy, imagine that you have a restaurant, which represents our system. And when you get a customer, their order is relayed to the kitchen. Now, at the moment, you have one chef, your head chef, who is making every dish in sequence as he gets it. Think of this as a simple client-server relationship. As your restaurant business grows, you can't have customers waiting for long periods of time for their food, of course. So being the good restaurant manager or system designer that you are, you hire a few more chefs. Now let's pretend for a minute that these chefs, rather than working together for some odd reason, are cooking orders from start to finish independently of one another. Think of this as having multiple servers and they're each handling requests as they come in, while that's better than your head chef working solo and handling it all on their own, this is also not efficient. And you've also got other issues to think about. For example, what if one chef works at a faster, slower pace than the others? What if one of your chefs doesn't cook certain kinds of food or dishes that your restaurant has? And what if one of your chefs takes a break and neglects their orders entirely, keeping in mind that they're currently not coordinating with each other? So maybe then you design a better system where you have certain chefs work as line cooks. For example, a couple focus on cooking the entrees, some do the sides, so on and so forth. And now your head chef is in charge of checking the time and progress of orders, sending out the food. Think at this point in the analogy, your head chef is the load balancer. And the rest of the kitchen staff are servers, computer servers. In system design speak, this is sometimes known as a server farm or a cluster. Basically, the setup is designed to handle a high volume and high variety of different requests in the most efficient way possible. So this is one way to think about load balancing. It's the intermediary process for how to best handle and distribute network traffic. So with that, objectives tonight, we'll be covering the following items in tonight's talk. We'll be defining, explaining the features of load balancers, identifying some common techniques for load balancing, and then looking at benefits and trade-offs. All right. So load balancing in general, this is the process or the ways that a system efficiently distributes traffic across its resources, or rather the system's resources. Their goal is to efficiently distribute incoming network traffic, things like clients' requests, to ensure fast and reliable responses. Load balancers are also actively monitoring the health of their servers, and they're dynamically adding and removing servers during periods of high traffic or in the event of server failure. Today, we see it especially really commonly in cloud computing, which we'll talk more about later. Hardware load balancers are common in things like data centers, and load balancing is a part of any modern large-scale web application. Load balancers are a part of those modern applications. Large-scale applications have to handle sometimes millions of user interactions at a time, and those users desire fast and reliable experiences. So load balancers play an important role in making that happen. Load balancers support scaling by adjusting the number of servers, as I mentioned, and handling traffic when it surges, especially preventing bottlenecks that is a server from being overloaded. They increase the availability and the reliability of an application or system. As mentioned, monitoring server health. Load balancers optimize resources and data transmission to make the user experience as good as it can be. So preventing things like sluggish responses or unresponsive applications. On the developer side, they can also support things like DevOps, a server that needs some maintenance or upkeep, for example. Load balancer will shift traffic to other servers while the server that needs maintenance gets worked on. Um, Load balancers also provide security. It's common for them to monitor and block malicious content, divert it to firewalls. Most importantly, they're a shield against things like distributed denial of service or DOS attacks, where high numbers of requests are made at the same time to try to overwhelm and cause a server to fail. And load balancers kind of help mitigate this by distributing those requests or, again, diverting them to places that can handle those attacks. And then overall, load balancers improve performance because they are rerouting client requests based on the ways that make the most sense. For example, this might be with respect to the kinds of requests that an application or system is receiving. It might be based on geography or location. It might be based on the servers and their capacities, their computing power. There's different ways to design them around those sorts of criteria. Um, yeah. So, moving on to types of load balancers. There are a number of types of load balancers. Just going to go over them briefly here. Hardware load balancers refer to the real physical devices. They're often housed in data centers. Think of sort of the typical big companies, your Amazons, your Googles. The equipment is highly efficient, very reliable, but also very expensive to purchase and maintain. And so out in the wild, you're more likely to encounter things like software and cloud-based or cloud-provided load balancers. Software load balancers are programs that are implemented into existing infrastructure, and they can divide and distribute traffic. And then cloud services, and you're relying on the provider's physical hardware. And so it's easily scalable, and you're using the service provider's hardware to do that. So it's great for dynamic and changing workloads, and they integrate well with cloud-based applications and other services. A couple other kinds of load balancing include network. A couple that are common you see are work at different layers in the OSI model. That is the model for different levels of network communication. The transport layer of load balancing looks at things like IP addresses and port numbers. So it's quick and easy to implement and sort of diverts traffic based on that. And then the application layer looks at specific data on requests, so things like cookies, URLs, headers, for more quality and complex routing. And then there's global load balancing too, which is based on things like server location or region where the application is. An example of this might be requests that get rerouted to somewhere else because of a server failure or maybe a server crash. All right, moving on to techniques. In the setup and configuration of load balancers, it's algorithms that are doing the work of directing all this traffic. And there are two broad categories, static and dynamic. And there are lots of algorithms within those two categories. We're just going to look at a few of them each here. First, with static load balancers, they rely on algorithms that are basically working with sort of a predetermined set of rules. Think of it sort of like a blueprint. They don't actively consider the current state of the system. They just use this blueprint to assign the workloads. It's easier to implement, but because they're not aware of the state and the condition of servers in real time, this can lead to inefficiencies and sometimes servers being under or overused. But a few of the common static load balancer algos that you see out there include the round robin. So you can kind of see with the diagrams. In the round robin, each server receives the request in rotating sequential order, kind of a circular repeating pattern. Again, this is typical of static techniques. It's simple. It's equally distributes the workload, low overhead to implement because it's only tracking the last server used. And it doesn't actively monitor server health. The cons would be it's not monitoring server health. So it may still overburden or overload a server that's at capacity, might be inefficient for dynamic environments where you need a lot of server adding and removal. The weighted round robin is pretty much the same thing, only into that sort of rule set, the developer would write in or sort of give weights to different servers, meaning that a server with more computing power or memory, for example, would handle maybe more requests, and ones with less capacity, less so. Con of this would, it still is not adapting to dynamic environments well, because again, it's not actively monitoring the state of servers in real time. And finally, for static techniques, the IP hash. This one is computing a hash on client IP addresses, and then mapping the requests to servers based on that. This is great for applications that use sessions or rely on state. Cons, though, it can lead to uneven server workloads. Also issues when a client is using multiple IP addresses. Switching real quick to dynamic techniques. Dynamic techniques, the algorithms here adapt to real-time monitoring of the actual traffic and the current condition and workload of servers. So the configuration is more complex, but they are generally way more responsive. So a few of those algorithms include least connection. Least connection method is distributing new requests based on which server has the fewest active connections. So this is great because it is effectively directing new traffic and new requests to the least busy server in that moment, which leads to a more balanced use of resources. Cons would be it's susceptible to spikes. It doesn't consider server capacity either, at least by itself. So a more powerful server might be handling fewer requests, while a less powerful one could be handling more, and that, of course, isn't optimal. There's also the least response time method, where we have active monitoring of response times based on time to first byte. So new requests are allocated to the server that has the shortest time to first byte. So time to first byte, that's all the time it takes to process the request, perhaps query the database if that's a part of the request, decryption or any other backend tasks, and then the time it takes to do those things and get that first byte back to the user. So the lower the TTFB, or basically the fastest response, that server will get new requests. This is great because it makes for fast responses, and it's really good for dynamic environments. User experience, though, can be affected if the server times fluctuate a lot, and there can be more overhead because it requires ongoing monitoring. So those are a few of the dynamic techniques that you see there out in the wild. Speaking of, these are also a few examples of load balancers that you're perhaps likely to see. F5 Big IP does both hardware and software load balancers. They were an example of a hardware that is common. HA Proxy and Nginx are examples of software load balancers. Nginx is also sometimes used as a proxy server, but it can also be configured for load balancing. And then thinking about our sort of big cloud service providers, think AWS, Google Cloud, Azure for Microsoft, all provide load balancing as a service. All right. To wrap things up, bit of summary of what we've covered. Load balancers, y'all are essential for any modern application or system that's operating at a large scale and it handles a lot of traffic. They do everything from supporting app or system performance, improving user experience by preventing disruptions or reducing response times, and they even support security. They're also flexible. They can be placed in different places throughout a system's architecture. They support scaling, especially with cloud-based load balancers that dynamically add and remove servers based on things like spikes in traffic or server failure. That said, like everything, there are no perfect tools, and there's some things to consider when it comes to load balancers. They are prone to the single point of failure problem. They're susceptible to that. So it's common to see them designed with multiple nodes, essentially multiple load balancers. And if, say, a primary one fails, traffic can shift to a secondary one and work can kind of continue seamlessly. Whether it's, new applications, mobile applications, the growth of cloud services, load balancers require updating and adapting to user requirements. And then algos for load balancing can become complex. So developers would need to be mindful of things like response speeds and migration time, which is the length of time it takes for one load balancer to shift traffic to another. All right, that is what I have on load balancers. Else is my works cited. Just want to say thank you all for your attention. Hopefully you're able to take away something about load balancing tonight. And I'd like to thank Scismic once again for sponsoring this tech talk. Thanks again, y'all.
Whoa, what an insightful and clear presentation on load balancers, Chris. Thank you so much for sharing your knowledge with us, and thank you everyone for joining us today. Hope you all have a wonderful rest of your day.